In this video, we'll look at the remainder of the SD rules. First one we'll look at is negation elimination. This is better known as proof by contradiction, or by its Latin name, reductio ad absurdum, which means reduction to absurdity. The idea is this: we assume that a sentence P is false for the sake of argument, and then if this leads to a contradiction, so a pair of sentences where one of them is the negation of the other one, if it leads to a contradiction, then what we conclude is that it's not possible for P to be false. So P must be true. That's the basic idea of the rule. So here's an example. If you don't clean up your toys, I will trip on them. If I do, I'll hurt myself. I'm not going to hurt myself. So you'll clean up your toys, right? So here's our symbolization key. And here's our derivation. So the premises are Milo doesn't clean up his toys. If he doesn't clean up his toys, then I will trip on them. If I trip on them, then I will hurt myself. And our third premise is I will not hurt myself. So to derive the conclusion here, we start off by assuming that Milo does not clean up his toys. Then, by conditional elimination from this line and line one, we can infer that I will trip on them. And then if if I trip on them, then from line two, I will hurt myself by conditional elimination again. And then we use reiteration to pull line three down into the subderivation. Now, the reason we need to use reiteration here is that what the negation elimination rule says is you need to have two sentences where one of them is a negation of the other. So they need to have this form Q and not Q. And they both need to be in the subderivation. And at this stage, right, the stage of line six, we have both of the sentences, but one of them is in the subderivation and one of them is up here. So we use reiteration just to get them both in the right place in the derivation, to get them both in the subderivation, which is where we need them. This is what reiteration is for, right? It's just for moving things around so that they're in the right place. That's really all you need it for. In fact, you have different derivation systems where you just rig up the rules slightly differently. You can actually get rid of reiteration entirely. Slightly different ways of setting up the rules means you never actually need to move things around. But the way that this system is designed, the way that these rules work, you do need to move things around occasionally. So we use reiteration to bring this in here, and now we've got H and not H in the subderivation, and so we can apply negation elimination. We infer C, so we strip the negation off of our assumption, and we cite this by citing this entire subderivation here from lines 4 to 7, negation elimination. Negation introduction is another form of proof by contradiction. It's basically the same thing, except it goes the other way. Whereas negation elimination, you have a negated assumption and then the rule strips the negation off. Here, you have an assumption and the rule adds a negation to it. So, for example, if a person transformed into a squirrel, then most of their mass would simply disappear. But mass can neither be created out of nothing or disappear into nothing. So people can't turn into squirrels. Here's our symbolization key. These are our premises. If a person transformed into a squirrel, then mass disappears into nothing. But mass cannot disappear into nothing, and mass cannot be created from nothing. So we assume, and again, this is an auxiliary assumption. We're assuming this for the sake of argument. We're supposing that a person transforms into a squirrel. Then by line one and conditional elimination, we conclude that mass has disappeared into nothing. But by conjunction elimination from line two, mass cannot disappear into nothing. We have a contradiction here with these two lines. And so we conclude that a person cannot turn into a squirrel. Now, here's an interesting problem. What happens if we have inconsistent assumptions? So take this, for example. Snow is white and snow is not white. That's an inconsistent assumption. Therefore, the moon is made of green cheese. Remember, in much earlier videos, right, we were talking about special cases of validity. And we said there that if the premises of an argument are inconsistent, then the premises of the argument can't all be true, which means then that it's not possible for the premises of the argument to all be true and the conclusion be false, which means then that the argument is technically valid, regardless of what the conclusion is. And that means, well, we'll see what that means for a derivation. So we're going to symbolize this. Here's the premise of our argument, S and not S. Now, in order to show that this argument is valid, we will assume that the moon is not made of green cheese for negation elimination. Then we use conjunction elimination to pull S and not S out of this premise here. We now have a contradiction in the subderivation, right? We've got a sentence and its negation. And so we can conclude M, that the moon is made of green cheese. This is known as the principle of explosion. Any sentence can be derived from inconsistent assumptions. If your assumptions are inconsistent, then any argument that you can get out of that is going to be valid. The next rule that we'll look at is called disjunction elimination. This is also known as constructive dilemma. This is the one of the primary rules for working with disjunctions. So the idea is this: you have a disjunction, and now the disjunction says that either P is true or Q is true. So what you do is you set up two subderivations. One of them you assume P, the other one you assume Q. If you can derive the same sentence in both of them, then you can infer that that sentence is true. So here's an example. Either the Republicans or the Democrats will win the next election. If the Republicans win, the US will be run by a bunch of billionaires. If the Democrats win, the US will be run by a different bunch of billionaires. So the US will be run by billionaires. In symbolizing this, the one thing to note here is in order to make this argument valid, because remember, when we're symbolizing, we want to try to make sure that we're setting this up in such a way that it's going to be a valid argument, if that was what was intended, was a valid argument. Bunch of billionaires, a different bunch of billionaires run by billionaires. We're going to symbolize all of these with the same sentence letter, because if you take these to all be separate sentence letters, you don't end up with a valid argument. If you suppose that they're all variant ways of stating the same thing, then you do end up with a valid argument. So this is going to be our symbolization key. This is the argument in standard form. And here's the derivation. These are our three premises. We start by our first subderivation, right? We assume that the Republicans win the next US election. And then by conditional elimination, we conclude that the US is run by a bunch of billionaires. The next subderivation, we suppose that the Democrats win the next US election. Then by conditional elimination again, we suppose that the US is run by a bunch of billionaires. Then by disjunction elimination, we conclude that the US will be run by a bunch of billionaires. And the way that you cite this rule is this. You cite the line that the initial disjunction is on. So we cite line 1 here. Then you cite both of the subderivations. So we cite 1, then 4 to 5, which is the first subderivation, then 6 to 7, which is the second one, and then or elimination. Okay. The last two rules we're not going to go through in detail. You've probably seen enough examples that you can know, you can figure out how these work on your own. These are the rules for the biconditional. And these both derive from the fact that P if and only if Q is truth functionally equivalent to if P then Q and if Q then P. So the biconditional introduction rule works like this. If you have a subderivation that starts with P and has Q somewhere in there, then you could conclude if P then Q. And if you had one that starts with Q and then has P somewhere in there, you could conclude if Q then P. So that would put you in a position to get this sentence, which means then that you can infer this, P if and only if Q. Likewise, the biconditional elimination rule is this. If you have P if and only if Q and P, then you can infer Q. But you can also go the other direction. If you have P if and only if Q and Q, you can infer P. So biconditional elimination is like conditional elimination, except it works in either direction. If you have either side of the biconditional, you can get the other side. Remember that conditional elimination does not go this way. If you have the antecedent of the conditional, then you can infer the consequent. But if you have the consequent of the conditional, you can't infer anything at all. That is the fallacy of affirming the consequent. So those are the rules of SD. In order to work derivations, you need to have all of these rules down pat. You can't win at chess if you're sitting there the whole time trying to remember how the knight moves. And it's going to be the same with SD. If your brain is overloaded with trying to remember what the rules are, then there's nothing left over for thinking about strategy and thinking about problem solving. So you need to learn the rules. You need to practice them with simple derivations until you get them all down pat. You need to do the self-assessment quizzes. And then once you've got this foundation down, then you're going to be ready to move on to doing something interesting, which is using SD to prove things. But first, you need to get that basis down, and you've got to make sure that you've got a solid grounding in the rules and a solid understanding of just what the rules are.